This is the second part of our exam skills masterclass. Today, we look at mathematical skills. If you remember last time, we looked at the assessment objectives. So I'm going to scroll through once again the slide. We understood the different objectives as well as, which is very important, the weight that they have on each paper. Okay, this is useful because apart that it prepares us in the type of content that we are assessed, but we also get, of course, some better understanding on the mark scheme and so on, and also how to study, as we looked at last time. We saw that like how to practice some different objectives. So the second one being the application of the content is a lot more difficult. So I talked about how we can practice it by having a lot of different resources, practice papers, exam boards. Okay, and now we will look at the mathematical skills. So I hope you had a chance to do some exam questions. And now we are at the math. In fact, 20% of the overall assessment of A-level chemistry will contain mathematical skills, equivalent to level 2 or above. We need to understand a bit what this means. Level 2 or above is GCSE Mathematics. So if you feel like you're stuck with the math of chemistry and you lose marks in simple mistakes of, I don't know, rearranging equations, or could be that you are just losing, or just you feel uncomfortable when you see mathematical skills. Yeah, it's a good place to start. Check GCSE Mathematics, just to have a little review of the key concept. Of course, you might not have time right now as you're preparing for the exams, but this is just to say, if you are this person that feels uncomfortable with the math, that feels like it's lacking some foundations, this is where we would start. Okay, so let's now take this into more details, and we will look at each mathematical skill that is required as it's stated from the AQA specification. Okay, so the first part, of course, and so we're going to do a little summary of the key skills. So you need to make sure you take a note of these things that you either don't remember or you need to consolidate, and we will look at also the application in some exam questions. So of course, the converting the units, from centimeter, decimeters, cube in chemistry, this is really the most important conversion that we need to do. So we need to remember how to do it. Also, writing it like this, I think it's quite nice. Divided by 1,000, one side, times by 1,000, the other side. Okay, I just want to add a point that very often we're asked to convert between meters cube and the centimeters cube. This is in the PV and RT gas equation, where if we use the pascals unit of pressure and meters cube the unit of volume, then we are likely to have to convert from centimeter to decimeter, so centimeters to meter. Okay, so because here is referring just to volumetric calculations. Okay, but would be the second objective, the application of your skills, these conversions. So as there is 1,000 difference between each unit, here there will be a 10 to the 6. So we can write it also times by 10 to the 6, positive and negative from centimeters cube to meters cube. Okay, so very important that you always check the units when you do, for example, as it says here, volumetric calculations, but I will suggest you to look also whenever there is volume stated in the question. And this is the first calculation. Second, recognize and mark use appropriate units in calculations. Well, the rate constant, equilibrium constant are very important here. Okay, so to calculate the units of both rate and equilibrium constant, it's specific for the type of reaction. So we need to work it out. Nothing to remember here, just I would always suggest you to do the working out on the paper. So write the expression for Kc. Well, if you remember how it is, also notice how here we're mixing up a lot of topics. It's a nice exam practice for you today. We will do the concentration of NO2 to the power of 2 divided by the concentration of NO to the power of 2 over oxygen. So it's a product over reactants. Now, you can include the units in this calculation, or you could write it in a different way, because we have the unit, which is the molar concentration, 2 at the bottom, 2 at the top, okay? So they cancel out, leaving 1 unit this way. Now, remembering that it's mole per decimeters cube, remember that, sorry, this is happening again. So it's mole per decimeters cube to the -1, because we can't have the unit as a fraction, so the unit would be mole -1 decimeters cube. So we need to expand the units all the time. Okay. Second, so the students carry out an experiment with the enthalpy change of combustion. So here, the next step is understand the different units are used in similar topic areas so that conversions may be necessary, entropy and enthalpy, okay? But also here, and I'm saying this example because it's the typical, it could be a step that we forget very easily, and it would be a silly marks to lose. But I want you to get used to really notice the units that you have in a question. So if here we have the enthalpy as a kilojoules per mole, when you calculate the energy of the reaction here, Q is equal to mc delta T, we'll calculate it into joules. Yeah? How do you know? Well, you would be given the specific heat capacity. Specific heat capacity is given in joules per Kelvin per mole. So you would know that your unit is in joules. So just by looking at the unit, notice how you will know the step of you have to divide to find the delta H. You will need to divide the Q by 1,000. In addition to, of course, dividing it by the moles, because you are given the data here to find the moles. This is just saying how the units are important. So as you notice, entropy and enthalpy, it should be straightforward, yeah, the conversion of the unit. So as you can see, you just have to notice the unit as you read the question, okay? And here, ignore this example down here, but when we talk about enthalpy and entropy, the equation involved is delta G is equal to delta H minus T delta S. So when we do this calculation, we needed to convert either unit, whichever you find it easier, into joules, into the same, okay? So here, I would suggest you to divide the enthalpy by 1,000 so that it would be kilojoules per mole per Kelvin, okay? It's a step that you cannot miss if you look at the question carefully, okay? Next part. Recognize and use expression in decimal and ordinary forms. So here you're tested on use an appropriate number of decimal places in calculations for pH. Okay. Here, the decimal, it's something that you have to notice in the question, okay, and significant figures as well, okay? So always read the question as you do it. Read it once you've completed to make sure that you've given your answer in the correct number of either significant figures or decimal places, okay? In this case, I think the calculation, it's, well, the point, the mathematical point is relatively easy, okay? If you wanted to give it a go to this question, pause and then play once you're done, because we'll go through the solution right now. The first thing, Ka, we have to have the expression down, and it's of this acid, so we know it's the product over the reactant. So the product is the dissociated acid, CO minus, divided by the weak acid, so C2H5COH. Okay? So here we have it's very important to remember the assumption that we make, that these two are the same, so that we can rearrange the equation. Actually, I'm gonna write down right away the numbers. If in the meantime you're doing it on your own, or you pause for it. So it's 1.35 times 10 to the minus 5 is equal to x to the power of 2, or you can write it as h plus to the power of 2, okay? Because we make the assumption that they're the same, and then 0.08 is the value, Okay, so let's do the calculation. X will be equal to the square root of 1.35 times 10 to the minus 5 times 0.08. Having this value, remember that the pH is equal to the negative logarithm of this value. So here, let's write it as concentration of H plus to make it more visual. And this should give you the right pH. Okay. So the pH should be 2.98. Okay, anyway, this is a very classic mathematical skill in chemistry. We continue with the second part. Carry out calculations using numbers in standard and ordinary form. Use of Avogadro's number. Okay, so here it means simply that we need to be confident with the bigger powers. Okay, and I really like calculation of Avogadro's constant because very often they are trickier than you expect. A very nice multiple choice to do. So I would suggest you to give it a go by pausing the video and play when you're ready to hear the solution. So apart of here, we're looking at the mathematical skills, with the powers and so on. This question is always so tricky because we tend to forget to do these moles ratio moles, right? So this is a trick question because you're given the moles of a molecule, but you're asked the number of atoms of something else. So it's the atoms of hydrogen inside of this molecule. So you need to look at the ratio, which is for every molecule, you have 6 hydrogens. So that's why you would have to times the Avogadro's number, which is 6.02 times 10 to the, we need to remember that 6.02 times 10 to the 23 number of atoms. So we would times it by the moles, and we should get this value. So it's important to think about these moles ratio moles. Okay, as I mentioned, worth to practice it because it will be an annoying mark to lose in the exam. Next question. Understand standard form when applied to areas such as but not limited to KW. Okay, so now standard forms are always important because when we deal with such big numbers, so when we deal with Ka, KW, because the dissociation, so here we're talking about KW, let's revise it. H plus OH minus, would be the other way around, but it dissociates to, so KW specifically, it's calculated as the concentration of H plus times the concentration of OH minus. We ignore the concentration of water because it's so much bigger. But the dissociation, it's so small that the number of the KW, it's very, very small. So that's why we needed to be confident with the standard forms, okay? And when we want to do calculations, of course, the concentrations will be also small numbers, but also Ka, if you remember the values of Ka, they're normally like times 10 to the minus 12 or minus 4. They're all, standard forms, so very important. But I think here is just about the skill to putting it right in the calculator. Okay, conversion between numbers in standard and ordinary forms, well, of course, it's extremely important, and I would suggest you to stick to one method in your paper, because when you write imagine, so this is very common when, for example, you have titration calculations and you have the moles in 25 centimeters cubed, the moles give you, for example, 2.1 times 10 to the minus 3. But then you need to convert it into 250 centimeters cubed. So this is common for titration calculations. And instead we write it as 0.021 moles. Okay, so of course, this is what the calculation may give you, and that's okay. But I would suggest you to stick maybe with one format only, because also very often you don't need to do some calculations in the calculator. But if you're doing, for example, a dilution and you just need to times something by 10, maybe avoid the calculator because using the power makes it equivalently easy. Okay, so this is my opinion on standard numbers and ordinary forms. Let's continue. Understanding significant figures. Okay, so significant figure, we'll talk about it a little bit later as well, but yeah, very important once again to keep the significant figures as well. Okay, so if you do it in one form and then you do it in the standard form, make sure you use the same significant figures, because otherwise you may get rounding errors, or yeah, rounding error could be a problem, or at the end you may give the wrong number of significant figures. So make sure to do that. Okay. We're the second part of the mathematical skills, so second objective, and we need to revise some calculations. Percentage yield. Percentage yield is calculated as the actual yield divided by the theoretical yield times by 100, okay? At the end, notice there are just fractions, okay? In fact, we will have the same calculation for the atom economy. All of these, remember, they're just fractions, like percentages of something. So maybe revisit a bit what is percentage yield, which is, as a definition, is the amount of product that you actually obtain compared to how much you were supposed to get. While what about the atom economy? The percentage atom economy is equal to the MR of the desired product over the total MR of the reactants. Again, times by 100. So think about it. What does it mean again? It's another fraction of how much of your product is present, like it's obtained, yeah, compared to the total amount that you've used. So it's about the conversion from your product, like from your reactant into the desired product. Of course, atom economy then gives us an idea of waste, so it's used a lot in discussions about sustainability. But in mathematical skills, notice how those are just the simple fractions, okay? Next one, construct the balanced equation using ratios. Okay, here it may seem like extremely simple. However, there are some questions that can be a little bit tricky. Okay, for example, one that comes to my mind and is one of the most difficult about ratios is when you're given like a reaction would, for example, a reaction like produces a certain mass X of carbon dioxide and a mass Y of water. Construct the balanced equation for the complete combustion of one hydrocarbon. Okay, so here you will need to find the ratios between each element in order to write down the like the amount of X and Y's. Okay, so this is what I mean in terms of finding the ratios. And what I don't have an example right here, but I would always suggest you to think about these moles, ratio moles, and knowing that at some point you would have to get the value of the moles. Okay, because ratio may also be like we see in the Avogadro's constant between the number of carbon in a carbon dioxide or the number of water in a water molecule. Okay, notice that that is different and it is relevant. Okay, so that's anyway, be aware of these balanced equations and this concept of moles, ratio moles. Okay, evaluate. So the third mathematical skills is estimate results. So student may be tested on their ability to evaluate the effect of changing experimental parameters on measurable values. Okay, so here is very specific for the value of Kc. Okay, and this is just an estimation of the result. Okay, and this is what is referring to is when you have the value of Kc, you know, you have let's call it C and D product over AB reactant. And you want to know what happens to the value of Kc as, for example, the temperature increases. Okay, you must know that the reaction is endothermic or exothermic. So let's say that the reaction is endothermic. You need to think about, okay, what mathematically what happens. So and I'm going to give you this example. If the reaction is endothermic, there is a temperature increase, means that the endothermic reaction is favored. That reaction is the forward reaction towards the products. So the product will increase. And this is the only factor that changes this ratio because it favors one reaction over the other. So if the value of the reactants increases, so does the Kc. Okay, that's what it refers to, and that's how we should estimate the result. Notice how I always explain it in a very nice and like simple, clear way, with some sketches that can really help keeping the logic. And this is the estimation of result. Fourth, mathematical skills. Use the calculators to find and use power, exponential, and logarithm functions. Okay, so here we needed to be clear with the logarithm and their and like also the relationship between all logarithms. Okay, and in fact, of course, this is for the topic of pH and pKa. So the equations that we must remember is that when there is a little p means negative logarithm of. So like the pH, the pKw will be calculated as the negative logarithm of the kW. And that's the pKw. Okay? What is tricky to remember is that, and I'm talking, referring here to the kW, just because we have the example there, the higher the value of kW, the lower the value of the pKw, okay? So there is this indirectly proportional relationship because it's a negative logarithm. Okay, so it's very important to have this clear. This is very helpful when we needed to think about pKa and the strength of acids. Okay, so that's why we need to understand this relationship. Okay, in fact, this is one of the relationship to know, but also when you want to find the value of kW and you're given the pKw, to revert the logarithm is 10 to the power of minus your pKw or your p-value. So these are the equations to know, because we will have to put it into also more intricate equations or questions like this one that is 4 mark. Okay, you could you could try if you want, because and then you can look back at the slides because the solutions are right here. Okay, so I will skip through, and this will be for you to try later on. Okay, next one is make appropriate mathematical approximations in buffer calculations. Wait, what does that mean? Well, anything that is involved in buffer. Okay, very important. And so buffer calculations, of course, can be, sorry, I'm checking here. Buffer calculations, they can be a little bit tricky because they involve some more calculations. So we need, first of all, to understand fully what is a buffer and how we would write it down. Okay, so when you have a question like this, I would always suggest you to have a bit more clear what is happening, because you don't understand really how the buffer is formed if you only have names like this. Okay, so I would always think it as, okay, we have butanoic acid, let's call it HA, but that's reacting with sodium hydroxide. So there is a chemical reaction taking place. It's actually a neutralization reaction. In fact, we will have this NaA and water. Okay, so of course this is going to be our salt. This is going to be our salt. Sorry, I'm not sure why this is happening. Okay, never mind. This is the salt value, and this is our acid. However, the acid is reacting. So the value that you're given here, so these two values of the butanoic acid, so to find actually the concentration of the acid that is present in this buffer solution, so let's call it in the buffer, you would have to calculate the HA value, which is the initial amount that you're given. So the initial would be these two values that are highlighted. But it's minus how much it reacted. So it would be minus the moles of the NaOH, because the NaOH has reacted with it. I hope you understand. This is a step that it's so easy to miss and to make a mistake of it, because we need to understand chemically what is happening. Okay, so mathematically, as you can see there, it's a bit extensive. There are quite a few steps. Okay, and then of course to find the concentration of the buffer, you would have to divide all of these, and sorry, here actually, I mean not the concentration, but actually the moles of your initial acid minus the moles of the base, and then all divided by the new total volume. Then the moles of the salt, which let's call it NaA, the concentration of the salt, would be the same as the moles of your NaOH. Sorry, my pen is going a bit weird. So it's the moles of NaOH divided by your total volume. Okay, because this is the limiting reactant. So this simply, like, as you can see, without the equation, I think it's easy to miss that is a chemical reaction that is taking place. So the moles of your buffers are actually less than, so the concentration of your acid has to be subtracted with the moles of what is reacted with. Okay, and then, well, we needed to have the Ka value written out, because, so the Ka equation written out, because we just need to think about the numbers that we have, because we would substitute everything. We can't make the assumption that H plus and A minus is the same, because it's different, because that comes from the salt. Okay, so this salt is the A minus, the concentration of A minus. Okay, and then we rearrange to find the H plus. I will rearrange it like this, which would be Ka times the concentration of HA divided by the concentration of A minus. So notice that these are all mathematical skills, rearranging the equations, summing up the true volumes. A lot of math here. And then, of course, the negative logarithm of this H plus will be our pH. Okay, so I hope you got the steps right, and I would invite you to find a value for it too. And I'm pretty sure the value is 4.93. Okay. Next mathematical skill, report calculation to appropriate number of significant figures. I think I talked about significant figures enough. And of course, notice how this is important. Here I've put a little summary from actually the AS Chemistry Crash Course, this extra worksheet that I include. And it's about using the correct number of significant figures. One thing that it's easy to forget is that we need to calculate, like the results that we calculate, they can be reported to the limits of the least accurate measurement. Okay, least accurate, least precise, because otherwise we would be using decimals that we can't guarantee that are these. Okay, so that's something that we needed to consider. So when they say appropriate number of significant figures, this is what to think about: the least precise and what's the maximum number of significant figures that has been used. Next part. We are handling data, so arithmetic means. So you will find calculation of means in, for example, the relative isotopic masses. Okay, here I would actually also invite you to try these questions. You know why? Because they're not as easy as they seem. I would include the calculation, and then I would invite you to try this question. The solution is on the next slide. But means, of course, here we're calculating isotopic, the relative atomic mass. So the equation would be the AR would be equal to, let's call it RR, which is the relative isotopic mass 1, times by the relative abundance of that isotope, plus the let's call it, no, let's keep it like this, the relative isotopic mass, actually let's call it IR, isotopic mass of the second isotopes times its relative abundance, and so on. And then also double check how much of the relative abundance you have, because here you have 100, so it's of course 400 atoms. But I've seen it before in a mass spectrum, so where you have to actually find the relative abundance of some isotopes, and here the relative abundance is not over 100, but it would be, the total of the peaks that you have. Okay, so it could also be a different number. No, don't forget it. And these calculations, they sometimes require tricky, actually quite a tricky rearrangement. In fact, here notice that the question is determine the relative isotopic mass of the third isotope of magnesium in the sample, which means that you have to set up an equation to find that relative isotope. So the mathematical skills involved here are more difficult than they seem. And so I would suggest you to never underlook these questions and always give it a go. So the mathematical skills are extremely important because, as we said at the beginning of the first part of the math, they're like 20% of your paper. And I will show more examples of calculations that are actually quite challenging and do require a bit of math skills. Like at the end, we finished with this part with finding arithmetic means, but it's not that simple. This specific calculation in this case is 2 marks, but it can be even maybe in a 3-mark question where you have to find the percentage abundance or the mass of one of the isotopes. So it's a bit more complicated because it's not just the simple average, yeah, but it will require a bit of arrangement. So if you haven't given a go yet, pause the video and play to see the solution. Otherwise, here it is. So what I want you to notice is how we have to give the unknown to one of the values. And also, if you feel like you're missing some values, well, the percentage abundance is always up to 100. So we can find the remaining one. In fact, this number is given as the difference between, or actually it's 100 minus the abundances that we already have. So it also requires quite a bit of interpretation, this question, not just pure, applying the numbers. Okay, so very important, worth practicing it. And then notice that it asked many significant figures, 5, because actually this is the number that we had here, 5 significant figures. So we have to keep it consistent. Okay, so always notice the number of significant figures. Let's continue. The next question, I would like you to give it a go maybe on your own time. So pause the video and play because you also have the answer here. Once again, this is the similar example of having to give an interpretation of these calculations a bit, just finding a mean and having to rearrange it. Okay, so make sure you give it a go. If you have any questions, then let me know later. Let's continue with with another part. So arithmetic means it's also found in titrations. So that's very classic calculation, and that just also because we're doing exam revision at the moment, I want to highlight some important things. Titration data is often given this way, so that you will need to find the titer, which will be the the final minus the initial value, and you will always have to consider when you calculate the mean titer the concordant results. Concordant results are within 0.1 centimeters cubed of each other. So it's very important to consider this because this, remember, it's equivalent to the uncertainty of the instrument. That's why we need to consider the numbers that are just this close, because this means that we kind of assume they're the same numbers. We just take into consideration the uncertainty. Okay, so of course, finding the mean here would be simple, but this is the important thing to remember. Okay, in fact, notice that it in the specification highlights the identification of outliers. Okay, sometimes you have nice questions in titrations too that they ask. This one could be like trial or rough titration, and you could be asked why that is important. And the reason is that it gives an idea of the amount of volume that is required. So you kind of overdo it. You don't stop at the slightest change in color, but just because so you have an idea of how much volume you need to add, so that you can get closer to the end point of titration, and only then add the solution drop by drop. Otherwise, if you do 22.5 centimeters cubed drop by drop, would take pretty long time. So that's the ribbon of the rough titration. Okay, means we're still into simple calculations. We're now into another one. Identify uncertainties in measurement and use a simple technique to determine uncertainty when data are combined. Very, very important. So the equation for uncertainty, and then I will give you a moment to try this. Remember that is. So the uncertainty, it's, well, it's calculated as the like the uncertainty of the instrument, which is the value that you're normally given, which is the plus or minus, times by the number of readings. Because you need to consider how many times you're using that instrument to find a value. In fact, then will be divided by the value. And then times by 100. So it's the uncertainty times the number of readings, which we can call it total uncertainty, divided by the value that you calculate, times by 100. Okay? So notice that in this question, you might need a little bit of interpretation when you look at, like, you have some volumes, you have some temperatures, you need to understand how many times you're doing this. Okay? So as I was saying, this question does require a bit of interpretation, because if you read the question, notice that the temperature of each solution is 19.5. But this means that we've measured the temperature of each solution. That's already twice measurement. And then we've mixed them together and we measured the final solution. So actually, how many times did you do the measurement? 3. So this means that, you've done, so this uncertainty of 0.5, we have to times it by 3 and then divide it by the value. The value that we calculate would be the difference between, so it's 36.0 minus 19.5. And if we times all of this by 100, it would actually give us 9.09%. So, but from the interpretation of the question, you will see that, you will see how many measurements you've taken. Okay, so it does take a little bit of interpretation. Okay, so important to understand the uncertainty calculation and then looking at the question carefully. Let's continue. We are looking at now another side of these mathematical skills, which is graphs. Okay, translate information between graphical, numerical, and algebraic forms. Okay, so many things that we need to do. And the first that I have in the slide is interpret and analyze spectra. Okay, the orders and the rate, we will see it a little bit later, but the analyzing the spectra, let's have a look at the spectra that you needed to be familiar with. So this is carbon, 13 NMR. This is hydrogen, NMR. This is infrared spectroscopy, and this is mass spectrometry. So those are all of the spectra that you need to be familiar with. Now, carbon and hydrogen NMR is the one that does require a little bit more understanding and knowledge, because it gives us structural information of organic molecules. Okay, and it's used together with the other techniques to get further information. In fact, the infrared, remember, the goal of it is to basically the main information that we'll get from this is the functional group present in the organic molecule. While the mass spectrometer, we use it, we've seen it in the atomic structure topic, and we can find the percentage abundance of the elements. But when we have bigger molecules, it's used to find the MR, these molecules. Okay, so in fact, the biggest peak, which is called the molecular ion, remember ion because of how the instrument works, the ion gives us the MR of the compound. We can get some structural information because the peaks are caused by fragmentation of the molecules, so we can still distinguish some structures, but it's not as useful, of course, as the carbon and the hydrogen NMR. That's why very often the spectra are used all together, so it's extremely important that you know which information you can get from each. Now, let's go with the next ones. Determine the order of a reaction from a graph and the rate expression from a graph. So here it's a little bit of revision from AS, AS, because you need to remember that the rate is calculated as the change in concentration, or in this case, it's mass. So I'm going to write it as change in mass divided by the change in time. Okay. So if you want to calculate, you can calculate the rate at some specific times for in this type of graph. If you do it at time 0, so the intercept with this line, and well, you do the tangent of at 0, this is called the initial rate. But if you calculate it, like in this case, at a specific time over here, you need to draw the tangent, and the rate here, it's called instantaneous rate. Because as you can see, is at specific time. Okay, now it also comes with a bit more interpretation questions, like describe and explain the change in rate during the first 200 seconds. And you may remember from the concept of collision theory, why the rate of reaction changes as the experiment occurs. And this is because of the change in concentration. And well, as the reaction takes place, there are less reactants present, therefore less chances of less frequency of successful collisions, because there are less particles. Therefore, the rate would start to decrease. This is, of course, assuming that the reactant that we're changing, and I'm calling it a reactant because notice that the mass decreases. Otherwise, the mass would increase if it was a product. And we're assuming that this has an effect on the rate of reaction. So year 13 students, you would know what I mean about that. In fact, would be the order and the rate expression, which is the more advanced part. Okay, so let's have a look at that. So this is actually where the other type of question that you could be asked, which is plot the variables from experimental data. Now, I'm not going to do it here because it's been more limited on the screen. So if you want to try it, I would suggest you to print it out, or maybe just have a past paper with an actual graph on it, or maybe you can use your iPad. Anyway, somewhere that it makes it a little bit more representative, of an actual graph on an exam paper. The important thing that you need to think about is to use as much as possible of the graph paper. Okay, so use numbers, any increments that make sense. Okay, so in this case, notice you have 50. Maybe you can use every 5, it's 50, and you need to count how many you have. Anyway, this takes a little bit of practice, okay? Or maybe you can use your ruler to help you, okay? So important to label the axis, okay? And then we'll plot them carefully using the ruler. Don't scribble around, but make sure you write like a little cross to make sure you're accurate, okay? And then, anyway, the point of the math skill is that you need to find the initial rate. And as I said, the initial rate is the one is the tangent of the line at time 0. And like this, you would find the initial rate of the reaction. So I hope I gave you a good idea, even though we're not doing, but I'm just explaining how actually to do these the graph. Okay, let's continue. So also with graph interpretation, we have determined the slope intercept of a linear graph. Okay, so well, this is also applied to these lines that we talked about now. These are the graphs, okay? And this is about the order of reaction. I'm going to scroll through because I do have examples of this, okay? So let me show you here an example. Anyway, remember that there are different orders. Let's do like that. To revise also a bit of the kinetic topic. Here, you could be tested in calculate the rate constant of a zero-order reaction by determination of the gradient of a concentration time graph. Okay, so concentration time graph, and here I'm going to do it exactly like you're not supposed to do it because you need to use rulers and so on. I'm still going to label the axis though. So we have concentration and time. Now, if it's a zero-order reaction, do you remember what that means? That means that the rate is not affected by the change in concentration. But the concentration will still change because if we assume it's a reactant, the concentration will decrease, meaning that we will have just a straight line. And because the rate doesn't change across, as the reaction occurs, this is as we know, it's a zero order. Okay. And of course, to find the rate, it would simply be the slope of the straight line. So this is what you could be asked to do. Okay. So calculate the rate. Nothing that so the slope then intercept the rate of change from a graph showing a linear relationship. Rate constant. Okay, so if you have zero order reaction, so let's think about what that means. A zero order reaction will be the rate. So, and here I'm writing the rate equation, which is equal to the rate constant times by the concentration of your reactant. But because that is at zero order, remember that the rate is equal to the rate constant. Okay, so if you need to find the rate constant, guess what? Would be the value of the rate, which is, as we saw in the graph before, the slope of that straight line. So this is a relationship that it's useful to remember. And of course, it depends on the type of reaction, if you have any other substance that affected the rate. But let's continue. Draw and use the slope of a tangent to a curve as a measure of rate of change. Determine the order of a reaction using the initial rate method. Okay, now here the initial rate method is the typical exercise that you would see where you have the you have several experiments, several concentrations and rates, and you need to determine the order of reaction looking at these initial rates. Okay, but I will open up an exercise later because I would like to practice a bit more challenging exercise with graphs and with specifically this topic, because this is one that students normally find a bit more challenging. Okay, because I don't know if you can recognize the equation. This is Arrhenius equation. So Arrhenius equation, this is used. I'm not sure why my parents doing this. Okay, never mind. The Arrhenius equation is used to find. So normally it's used to find the activation energy of a reaction, because as you notice, I mean, Arrhenius equation looks a bit different than this. Arrhenius equation is calculated as, so we'll have the rate constant, or the rate is proportional to or is equal to this is the Arrhenius constant, is like a collision theory the collision constant, doesn't matter, it's just a constant, exponential of minus activation energy divided by RT. Now, let's think a little bit about how these translate at the end to a linear graph. Well, if we take the natural logarithm of this equation, we remove the exponential and we get this. Now, 1 over temperature, the rate constant, as you can see, this point is very important. The rate constant K is directly proportional to 1 over T. Okay, so instead of K, we write 1 over T, but we've taken the natural logarithm of all of it. So as you can see, would be the natural logarithm of the rate constant, natural logarithm of the collision factor, and then we've removed the exponential. Okay, so as you plot the x-axis 1 over T and 1 over, so the natural logarithm of 1 over time, so this is temperature, this is time, you will get a straight line. This straight line will have a negative slope. This negative slope corresponds to the gradient, which is, I'm going to write it here, minus EA over RT. So if the value of the gradient is this, how do you find the activation energy? In fact, this is what the question asks. So to find the activation energy, you will need to do. So I'm going to write it over here. The activation energy is equal to your gradient times by RT. And then, of course, it would be a positive value because, as we know, the activation energy is positive, and also if you do the correct rearrangement, it will give you a positive. So this is, as you can see, a little bit more advanced graphical interpretation, and sometimes this exercise comes also with a bit of calculation here. But I would invite you to write it down, maybe looking carefully at the scale that has been used in this graph. You can do it on your paper because in the next slide we have the solution. So if you want to give it a go, pause now and play when you're ready. Okay, so I hope you gave it a go to this question, and then here is the solution. So I hope your graph looks similar to this, the gradient as well. Okay, if not, take your time to spot where you did mistakes, maybe in how you did the graph, or maybe in some of the data. Let's continue with the next part. Now we are at the geometry and trigonometry. Use angle and shapes in regular 2D and 3D structures. Now, guess which topic I'm talking about? I'm talking about shapes of and bond angles in molecules with and without lone pairs, for example, ammonia, CH4, and water. Okay, why don't you pause the video and give it a go? This is an extremely important topic from year 12, but that it will recur in all of your A-level papers. So I would highly suggest you to try before I go through the solutions. So the shape, the first one, and let's see if you got it right. The first one is a tetrahedral. Why? Because okay, I will just quickly do it. I like to do it with the dot and cross diagram. So we have 5 electrons for nitrogens, but because we have an NH4 plus, I'm going to consider the electron missing there, even though this is not representative of the actual bonding, but it makes it a lot easier for the shape. And then there are 4 hydrogens, so this is simply how it's going to be. Exactly, no lone pairs, and here we should put it. Okay, remember this is not what normally happens because H plus is actually the hydrogen that is H plus, but notice how easy it makes it with the dot and cross diagram. While the NH2 minus, well, I would use the same concept. Nitrogen's 5 electrons. I would add the extra electron from negative charge in the middle, and then I would add just the 2 others. So that is exactly nonlinear or bent shape. So tetrahedral, nonlinear bend, the bond angle is 109.5 for tetrahedral, and we have 104.5 because we have 2 lone pairs. So also, of course, this is an important topic to be able to describe, to discuss it, because you are often asked to explain the bond angle, and that's always relative to the Vespers theory. And that theory, remember, is because of the repulsion between lone pairs. It's greater than the repulsion between lone pair and bond pair. So make sure you're confident in describing this way. Next one. Identify chiral centers from 2D and 3D representation. This is for year 13. And I would suggest you to give it a go because it's very important that you actually get the drawing when you do this type of questions. Okay, so first I would actually start with drawing this out, displayed formula. It is helpful when you want to convert the structural formula into something a bit more easy to see, and that is this. Yes, so the type of stereoisomer, the type, you need to call it optical isomer. Why? Because there is a chiral center in this carbon. Okay, the explanation would be about the chiral center, and we have to explain it as there are 4 different groups around the carbon. Okay, and the 3D diagram, remember, it would always be with the focus of the chiral center. So I would always write it in the tetrahedral structure. And then you can just write around it the groups involved, okay? Remember that all of these groups could be written just as it's written here, okay, in the structural formula. But it's very important to start from this, which is the chiral center, okay? And I hope the reason of chiral center makes sense. Okay, one more for you to try. Actually, this is a 6 marker, and I would suggest you to pause the video and take your time to do it because it's a 6 marks. Let me write a little note over here. And there is quite a lot to digest in this question. Choose structures that you're not familiar with, that looks a bit complex, and remember that this is the typical second objective where you have unfamiliar examples and you need to apply your knowledge. So please pause the video and give it a go. And when you play, I will show you the solution. So I hope you tried this question. Here is the solution. Okay, the isomers that are present here are again, stereoisomers, but this time the geometrical ones. Okay, as you notice, geometricals can be E or Z, so we have to label them as well. Okay, we also notice that there is a chiral center at carbon 3 for this other molecule. Okay, and therefore we would have to state which type of isomer that is. Okay, and the 3D images may look a bit more complicated, as you can see from the mark scheme, but notice how at the end we always take the chiral center and convert that into tetrahedral structure. So you always, and the tetrahedral, they have the common shape of 2 lines that are at the plane. Oh, I have it here. Like 2 that are actually at the same plane as the paper, and then one coming towards you and one coming behind you. Okay, that's how it is. Okay, notice that we've just put that into this molecule. And of course, remember that these are mirror images of one another because optical isomers can have mirror images. So they're called the stereoisomers. You can call them this way as well. Yeah, or enantiomers if you want to use the specific words. Reason, they are non-superimposable mirror image of one another. Okay, let's continue because there is a lot in this topic. We've seen optical isomers, we've seen geometrical isomers. Here is another one. And here we link it with the isomers of transition metals. And I would suggest you again to pause the video and try to actually draw it out. Here it's extremely important that you get confident into the drawing. So give it a go and then I will draw it with you. So for this, for the transition metal complexes, well, you know the common shapes. So I would always suggest you to start with like the skeleton. Actually, here we have iron, so I can write it as iron. I was going with a general metal. So we know that iron, it has, well, it says also here that with the 3 ethanothionate ions, so the coordination number, it would be 6. So it would be iron with the 6 bonds. Now, we know that the general shape, and I will always start like this. We have the 2 bonds, one at the top, one at the bottom, and then the square planar, the horizontal plane with, you know, this perspective that, you know, comes towards us and away from us. Now, then we know that the ethanothionate ions will form, you know, will link, is a bidentate ligand, so it would join in this way. So the mirror image of this, we can just, I would always suggest you to start with one, and then you literally just do the mirror image. The mirror image would be, okay, we have iron like this. You just have to draw this same skeleton. Sorry, it doesn't look very good. Sometimes it goes crazy. Okay, like this. And then, well, how is it the mirror image? Well, those 2 are connected. Those 2 are connected. And then these 2. So very important, and the overall charge, we do need to put that into, so we need to put it in bracket. And then we need to put the overall charge. Now, if we have iron 3+, and it has the coordination of these COO ligands, and we have 3 of them, okay? We will put them into, actually it will be COO2. We could write it like this, or yeah, I think like this is fine. Or normally you can write it as EN, which is normally the best way. If we have 3 EN, then the overall charge would be like this. We know the iron is 3+, each EN is 2+, so the total charge would be 6 minus, so the overall charge would be 4 minus. We write it like that. Okay, so 3D shapes of the optical isomers because they're non-superimposable mirror images. Okay, structures of the ethandiolate ligands and overall charges. Now, notice that the question is asking, show the structure of the ethandiolate ligand. So it's not like I draw it. I wouldn't get the marks. You would have to draw it exactly as the oxygen is bonded here. And then you need to follow the same, you have to follow the same lines, okay? It takes a bit of practice. That's why I'm saying it's very important that you do practice writing down it, because also the molecule does have to look, you know, the shape has to be like not kind of distorted, you know? So make sure you practice, okay? But if you had to explain it very quickly, the structure as I did would be okay, but not like in this case that asks specifically the structure of the ligands. Okay, I hope you did it better than I did, but I hope you still understand my explanation. And now I will show you also another 6-mark question. So pause and make sure you try it. Draw the stereoisomers of the catalyst and determine whether each stereoisomer has an enantiomer. Here it's a lot of drawing practice. So make sure you give it a go. You don't skip it because I know it's a lot of work. So this is what 6 marks look like in this question. As you can see, we start with the skeleton and we just move around the ligands. Okay, none of this has an enantiomer. Why? Well, because there is no mirror image. As simple as that. Okay, I hope you got this. Yeah, and I hope you got a bit more confident in drawing them out. Here is another question where we have to identify chiral center. As you can see, this is a very important topic, and in this specific one, it's very likely that you get examples that you're completely not familiar, so don't get scared if in the exam you see these type of molecules where they look big and complex, okay? So just make sure you know what a chiral center is, and you slowly identify it. Okay, so which one is the chiral center? 3 chiral centers, okay? And it takes observation skills, so make sure you slowly go through the molecule and imagine what is attached, okay? You can also like imagine that we know that we don't put the hydrogen, so if there are just the 2 bonds, we know that 2 others will be hydrogen, so won't be chiral center, and also we ignore the double bonds completely. Okay, so I hope you got it, and I hope your math skills went better. Next time, we continue with the practical skills. Okay.